All right, the beginning's a new arc length to deal with. This particular arc length is this is a great deal. The last time we did it was something, with the square root of 1 plus f prime of x squared. You can kind of see f prime of x, or think of that as y, dy dt here, something similar to that. And that was traditional arc length. This is a relative similar derivation of that. But in general, I think this is actually a pretty nice connection to where on earth we get arc length from anyway. So arc length is the distance along a particular arc. Well, you would approximate it with a whole bunch of little tiny segments. So, if any particular segment I throw in there, and then to make it more accurate, you add in more of those segments, infinitely small little segments, and then add them all up. And of course, that's what an integral is adding up all those little segments along the way. So let's take one of those little segments, and we know that arc length, or maybe do it from this side, arc length is, the distance between things is, kind of reverse Pythagorean theorem. We would do difference in your x's squared plus your differences in your y's squared. And the difference is, sometimes we would maybe call that dx or something like that, or delta x. So that's probably a good way to look at it. It's delta x squared plus delta y squared, the square root of that. It's just Pythagorean theorem. You're finding a squared plus b squared equals c squared if you turn this little dude into a little right triangle. And delta, change in y and change in x, thinking of a differential as some way of describing change in y and change in x with respect to time. Then you can see basically this is delta x squared and delta y squared. So that's the roots of this particular function. Very handy for the stuff that we do next. All right, so now we get to put it to use. So if I take these two functions, basically we're going to take the derivative of each, the x and the y, and square it, put it under the radical, and do the integral from, in this case, 0 to 1 per that t interval you see on the right. Now, the process of doing that, not a big deal. There's some algebra in here that gets a little bit tricky, but there's your basic setup. And if you had a calculator section, you certainly could put this in and resolve it right away. But without a calculator, then we're going to have to go a little bit further. But we could be done if we had a calculator. So a little simplifying, 2t squared, the derivative of t squared, and 2t, and the derivative of 4t cubed minus 1 was just 12t squared. Hopefully that's evident to you. Square each of those, add them, and distribute the squared, and I get the following. Now, I can't integrate that as is, but if you can imagine, since we have that radical there, if we can just do some factoring of some kind to get that radical employed, that might be helpful. What they have in common, you'll notice, is a 4t squared, so we can at least divide that piece out. That leaves 1 plus 36t squared behind. And you'll notice in there, that's not too bad, but if you have a product like that, you can take the square root individually. So square root of 4t squared, perfect square, we can get 2t. And with that, that's a little bit better. Now the next piece, we can factor out that 2 and take a closer look. You got some u substitution going on there. So because the internal 1 plus 3t squared, the derivative of that is a multiple of t, our external piece, so that's a candidate for u substitution. So we go ahead and run with that. There's u equals 1 plus 36t squared. Do a little solving and get your t there. So this is just a quick through that runs that u substitution. If you can see that. Again, I'm just going a little bit quicker here, but 1/72 du equals t, and then substitute those. Integral of u to the 1/2 is u to the 3/2 over 3/2, or you can multiply by the reciprocal 2/3. The 1/36 comes from 2 times 1 over 72. And then put u back and do some simplifying there. Sorry, this little tiny down in the corner there, but ultimately we get 1/54 from multiplying 2/3 times 1/36. And then the internal 1 plus 36t squared, all to the 3/2. We're going to evaluate from 0 to 1. So we'll put in 1, get 37 to the 3/2, put in 0, and we get 1 to the 3/2. And that's the story. That's the length of that particular segment when time goes from 0 to 1. The only thing about an arc length is that you remember it is a distance, so it's going to be positive. So you just want to be sure you account for that. It is a positive result that we have. All right, next big piece. All right, so sorry, there's a little a jump in this video to some random place. I actually lost track of where I was when I was recording it, so hopefully this is relatively sequential. Anyhow, what we have now is this idea of horizontal vertical velocity components and vectors. So I don't know what your experience is with vectors, if you did some in physics or pre-calc or anything like that, but
The basic idea is that motion along a curve has both a horizontal and vertical component, like you're moving in a direction. So those blue lines there, the horizontal component, left and right, and up and down component. Anytime something's lofted into the air, there's a motion vertically and horizontally that you can measure, and the length of those little arrows, those blue arrows, those are the vector components. They represent how fast it's moving in a given direction. In fact, if I were to redraw this one here, where it's located, the point that I've notated here, frankly, I should probably make that shorter, because you notice there it's kind of a lateral horizontal motion taking place there. So that would mean that vertical component of the velocity at that moment there should probably be smaller than what I'd written in there. But anyhow, so if we keep going, dy dt and dx dt are those vertical and horizontal components. Sometimes use the prime notation, but you'll see that here, that's what we've got in the first two components here. You're talking about horizontal and vertical components of velocity. What we'll talk about later is the general motion of velocity and that resultant vector. But there's a position vector, s, and we use that cool notation with kind of like an arrow to the right, but missing half of its point, the top and bottom half. But that's vector notation. These chevrons, I love that word chevron. Take a look down here. That's one notation for vectors. It's nice because it kind of looks like sideways V's, so you think of that as vectors. But you can use parentheses too, and just be careful that the context is about vectors. Then velocity, first derivative of each, acceleration, second derivative of each, so pretty easy to read. Down at the bottom, we have dy dx is the rate of change of y with respect to x. In other words, the tangent line with respect. So that's the tangent line slope on a curve. So anywhere along there, if you put up a tangent line, that dy dx represents the slope of that tangent line. All right, on to the next piece. So what you're going to notice is that this is all kind of old. The dy dx we just talked about, second derivative, d squared y, you take the derivative of dy dx over, we have that, dx dt that we have to remember when we're doing that derivative. And I'm going to delete some of those weird markings that showed up here. This next piece, this norm vector, the speed of a particle, or the magnitude or length of the norm of the velocity vector. So these are just all synonyms for this type of thing. So if you remember velocity, that v of t, and we're using that vector notation, so we're saying, v vector notation, oops, I'm pretty bad at writing that, of t, that's your velocity vector, that's forward and backward, that has direction. You put the absolute values on there, and we're talking speed, just the magnitude or the length of the norm of the velocity vector. So norm ends up being the terminology often used, norm and magnitude. It represents that absolute value, that speed resultant vector of how fast you're moving in a particular direction. Now, here's the fun part. So let's take a look at this. Does this look familiar at all to you right here? Okay. Well, velocity, let's put it in context here. If I actually draw a curve, we can put something in here like this. If we're interested in, well, maybe I shouldn't talk about a curve. Let me undo that. Let's just talk about some vectors for a second here. Get these vectors looking pretty good. There we go. The idea when we're trying to figure out how fast something is moving, well, these two vectors. This is the the dy dt, the vertical piece, and then the dx dt. Your horizontal is supposed to be a t. It does not look like a t, but just trust me, I'm trying to draw t's. So we get the vertical and the horizontal component. To get the resultant, this velocity vector, this speed of the particle, the norm vector, or the norm of the velocity vector, what we tend to do is we take that piece on the left and we shift it over. So we take this one and move it over to the left, so I move it over there. Okay, you see that happened right there. And we put it on the end of, or the head of, the horizontal vector. And the resultant norm of the velocity vector is this dude right here, is when you connect the diagonal point of it. Here is the norm vector, norm of the vector, velocity vector, that I have written over here. Norm of the velocity vector, we think of the speed of the particle, so on and so forth. So that's the norm of the velocity. And we use, of course, that notation over here. It's that absolute value of the velocity vector, v of t. And It's can be found by, well, can you imagine that's kind of a right triangle? We use a little Pythagorean theorem in there. Check this out. Because you know the vertical piece and the horizontal piece are dx and dy. I don't know if that's respectively, if I said that in the right order or not. But I could do dy dt squared plus dx dt squared. Okay, that would be the would be equal to, that length squared. So we take the square root to get the length of that norm vector. So hey, we're talking about that velocity vector again. And get the square root of dy dx or dy dt squared plus dx dt squared. Now, we've talked about this as if we integrate this, that is, if we go along a curve and measure little segments along the way, if we do an infinite number of, remember the curve for arc length we just took in, get a different color rock in here for a second. If we take little segments along the way to kind of mimic the whole curve, arc length is a sum of infinitely small little pieces like that, and then we just did a bunch of little right triangles to calculate the length of those little pieces. So this is kind of that same context. If you integrate that Pythagorean theorem piece, you get the length of that piece. So it should look kind of familiar. So there we are. That's the resultant vector. Integrating that is your idea of how fast it's moving. There's more to it than that. Because when I talk about, do you remember, if you guys take the integral of, this is just another side, but a good one as we're reviewing anyhow, if you take the integral of velocity, v of t dt, ooh, let's fix that. Do you remember the result you get from that? If you take the integral of velocity, remember that's displacement, because you're talking about forward and backward motion. It has direction to it. So, you can have forward motion and backward motion. They can cancel with each other. One's positive, one's negative. That would be displacement, how far you are from your original location. As opposed to if you do the integral of speed, which is what we're dealing with, we do the integral of speed, dt, which would be the absolute value of velocity. So maybe I should write that. I use the word speed, but we could do the absolute value of velocity. That gives you just the ultimate magnitude. Then we've got ourselves like total distance traveled. I'm just trying to show you some correlations there between the type of work that we're doing and some of the concepts that we've dealt with in the past. But isn't that slick? You got total distance traveled, this kind of norm vector, the length of that, tying it back into something that we already know. And then right below, of course, I wrote in here, there's your arc length, just so you get they are tied into each other as a sense of measuring a distance of a segment, but an integral, an infinite number of those little lengths of the Pythagorean theorem, and you got your arc length along an entire curve on the interval a to b. All these are just summation of, you probably get the idea with most of these, but just some filling in the gaps, enrichment type things that go with it. So if you remember, down at the bottom, total distance traveled, integral of absolute value, whether in a straight line or in a curve.